plus 3 is equal to 11. And for G1, we have 5 plus 9 that is equal to 14. And we have to add it to heuristic measure of node G1. But because node G1 is a goal node, its heuristic measure is 0, so 14 plus 0 is equal to 14, single edge. And we say the heuristic measure for reaching this node G is Hn. And another way is using intermediate node n prime. Hey everybody, welcome back to Artificial Intelligence course in Farzin Academy YouTube channel. Today we want to continue our search course in Artificial Intelligence in heuristic search algorithms, and today we want to talk about a star search. If you remember from the previous video, we started a new chapter of informed search algorithms, a new kind of search algorithms in comparison of uninformed, and this is because we have some extra information about our graph or our search space, and that would be our heuristic function or our heuristic measure. That is an estimation of the cost of shortest path from state n to the goal node. So in the previous video, we talked about GBFS or greedy best first search, and today in continue of this process, we want to see how a star search algorithm works. So if you want to watch the previous videos of this course, I provide the link of playlist in the description of the current video. All you have to do is click on the link and all videos will be shown and you can watch the previous videos. So let's continue and see how we have to choose our next node to building our search tree when we're applying a star search algorithm on our search space. So first of all, because this algorithm is heuristic or informed, we have to know how our evaluation function behaves. So this is the way that we calculate our evaluation function. All we have to do is adding our heuristic measure to a new function gn. So this gn is very simple. This is the cost from the start state to the node n if we want to calculate gn. So what does it mean? Consider this simple example. Consider I have my initial node here S. It has two children, A and B. From A, I have two another children, C and D. So consider this cost is 5, this cost is 4. Here is 8 and here is 3. So let's calculate the function of g for each node in this function. For example, if I want to calculate gc, it means the cost from our initial state to reach node C. So the path to reach this node is S to A and A to C. So for reaching A from S, it would cost for 5. And for reaching C from A, it would cost 8. So the value of function g for node C is 13. It means we have to pay 13 to reach node C from our starting node. Or for example, consider we want to calculate this value for node D. I say the value of g for node D is the total cost that I have to pay from my initial state to reach node D. So this is 5 plus 3. That is equal to 8. So I think now you know how we calculate the function g for each node. And the way that we calculate evaluation function for a star search algorithm is adding our heuristic measure to this function. And based on this, we have to choose the node with the least value of f, our evaluation function. So let's see how we can apply this algorithm on our directed weighted graph down. So like always, I separate my screen into two sides. On the left side, I have my graph, and on the right side, I want to build my search tree. And like always, I want to use a visited list to keep track of nodes that I expanded to prevent any duplication. So let's start it. Like always, we have to start from our initial state, node S. So node S here, and I want to write my evaluation function value of each node next to it. So for node S, this is 5. Let's see, my evaluation function Fn is Hn plus Gn. So for node S, my H value is 5, and my G value, because we are in the starting node, the value of G for node S is 0. So my F would be equal to 5 for node S. So this is how I write down 5 here. So let's continue. I have to expand this node because this is the only node that I have. So based on the graph on the left side, node S has 3 children, node A, node B, and node D. So I expand it and mark node S and add it to my visited list. And now I have to calculate the evaluation value for each node. For node A, we say what is the value of G because we have only one edge between our initial state and node A. Our total value of G would be 5, and we have to add it to heuristic measure of A. So heuristic measure of A is 7. So it would be 12 for node A. And for node B, our value for G is 9, and the heuristic measure of B is 3. So 9 plus 3 is equal to 12 too. And finally, for node D, the value of G, the cost of this edge, is 6, and the heuristic measure of node D is 6 too. So if we add 6 to 6, it is equal to 12. So for all 3 nodes, my evaluation value is 12. So I said we have to choose the node with the least value of Fn. But here, all nodes are equal. So I have to pick one node randomly. So consider I choose node A and expand this node. Based on the graph on the left side, node A has 2 children, node G1 and node B. So I write them here, and because I expanded the node A, I mark it and add it to my visited list. After that, I have to calculate the evaluation value for nodes B and G1. So for node B, the value of G is the total cost of the path that we reach B from S. So that would be 5 plus 3, that is equal to 8. And we have to add 8 to the heuristic measure of B, that is 3. So 8 plus 3 is equal to 11. And for G1, we have 5 plus 9, that is equal to 14. And we have to add it to heuristic measure of node G1. But because node G1 is a goal node, its heuristic measure is 0, so 14 plus 0 is equal to 14. So here I have 4 nodes that I can pick them to expand. 2 nodes of B, 1 G1 and 1 D. Based on a star search algorithm, I have to choose the node with the least value of F. That would be node B with evaluation measure of 11. So I expand node B based on the graph on the left side. Node B has 2 children, node A and node C. So I mark node B and add it to my visited list. After that, I have to calculate the evaluation function for node A and C. For node A, that would be equal to 5. Let's write it here. 5 plus 3 plus 2 plus heuristic value of node A. So for node A is 7. So that would be equal to 17. And for node C, I have 5 plus 3 plus 1 and plus heuristic measure of node C, that is equal to 4. that would be equal to 13. I have 9 here, plus 4 is 13. So I have to choose the node with the least value of evaluation function. So I have two 12s. I have to randomly pick one. So consider I want to pick node B. But the point is, node B is already in my visited list. It means it would be reluctant move to expand node B because it's already expanded. So I say this node is a dead end. So I have to go for node D. For node D, based on the graph on the left side, I have three children, node C, node E, and node S. So I say node D is expanded, I mark it and add it to my visited list. After that, I have to calculate the evaluation function for each node. For node C, that would be equal to 6 plus 2 plus heuristic value of node C, that is 4. So it equals to 12. For node E, it's equal to 6 plus 2 plus evaluation value of node E, 5. That is equal to 13. And finally, for node S, we have 6 plus 1, 7, plus 5, that is equal to 12, 2. So now, I have nodes, and actually node A would be ended in a dead end because node A is already in my visited list. So my candidates for expansion is C, G1, C, A, and S. So I have two nodes with value of 12. That is the least value I can find here. So consider if I want to expand node S. Node S is already in my visited list, so I won't expand it. So my final candidate would be node C with value of 12. I expand it based on the graph on the left side. Node C has two children, G2 and S. So I write down G2 or F, excuse me, and another S, and because S is already in my visited list and I said this would be end in a dead end, I don't write down S here. So I just write two children of C that there's a possibility to expand them, G2 and F. And I have to calculate the evaluation function for each node. And this would be an easy way to calculate, but first let's mark C and add it to my visited list. After that, for calculating the value of evaluation function, for G2, I say 6 plus 2 plus 5 plus evaluation value, heuristic value of G2, but G2 is a goal node, so it's 0. The final value would be 13, so I write 13 here. And for F, I say 6 plus 2 plus 7 plus heuristic value of F, that is equal to 6. And the final answer would be 21. So I write 21 here. So let's see what nodes I can choose to expand. One node is node C with value of 13, G1 with 14, G2 with 13, F with 21, and E with 13. So I have three 13s and I have to pick one randomly. So consider I pick node G2, but node G2 is one of the goal nodes. That means my algorithm is done here, my search is done here, and I've just found a path to my solution. So the path that we find is node S to D, D to C, and C to G2 right here. And what is the cost of this path? S to D with cost of 6, D to C with cost of 2, and C to G2 with cost of 5, that is equal to 13. And the fact is, this is an optimal solution because A star search is optimal. Well, we will talk about it. So let's go further. Talk about A star search properties. We say this algorithm A star is complete and optimal if heuristic function satisfies the following two conditions. There are two important conditions that we have to be familiar with to realizing if A star could be complete and optimal or not. The first condition is admissibility. We say our heuristic function must be admissible. It means the value of heuristic function is less than or equal to the actual cost. Or we can write it here. Hn is less than or equal to actual cost. This is the first condition. We call it admissibility, and we say heuristic function must be admissible. The second condition is consistency. We say heuristic measure must be consistent. It means we have to satisfy the triangle inequality. So what is triangle inequality? I write down it here. Consider this simple schematic. I have 3 nodes. I want to reach node G. I have 2 ways. My source is node N and my destination is node G. So one way is going to node G from N directly with this single edge, and we say the heuristic measure for reaching this node G is Hn. And another way is using intermediate node N prime, going to N prime with cost of Cn N prime. This is the actual cost, not a heuristic measure. And we go from N prime to G with heuristic measure of H N prime. So we call the triangle inequality satisfies if the value of heuristic measure for N to G is less than or equal to sum of this actual cost and H of N prime. It means going to node G from N directly must be a better way to go to G with using an intermediate node of N prime. We call it consistency, and if this situation satisfies, we call our heuristic function consistent. And for the final hint, we say every consistent heuristic is admissible. It means if you can prove your heuristic function is consistent, you're already proved that it's admissible too. But if you prove your heuristic function is admissible, you have to prove its consistency too. So this is the end of this video. If you enjoy it, it would be a big help for me and my channel to like this video, share it with your friends who are interested in AI and computer science, and subscribe my channel. Thank you very much. See you later.